Okay, let's tackle problem 4. So in this problem we have a stack. It's emitting a plume over a rural area at 150 grams per second on a cloudy night with a surface wind speed, and notice these quotes here, so this should trigger something. Anytime we say surface wind speed, that should trigger us to know that this is at a z of 10 meters, so above ground, 10 meters. And then we know that the stack has a physical height h of 80 meters, an inner diameter of 2.5 meters, a stack gas velocity of 20 meters per second, and a heat emissions rate of 30,000 kilojoules per second. And we're also given some tables to use. So first of all, we want to copy out, some of the details from up here so we know what we're working with, what information we have. So first of all, our flow rate is, this is kind of our mass emissions rate in this case. And so this is 150 grams per second. So notice that usually we use that m with a dot here, but for these equations they use the q as their mass emissions rate from the plume. So just make a note of that notation that's a little bit different here. So we're going to convert this into micrograms per second because that makes things a little bit easier for us further down the road. So we have now got our Q in terms of micrograms per second, and this is an S. And then we're going to pick out our surface wind speeds and note that this is at 10 meters, is 3.2 meters per second. Our height of our stack is 80 meters. The diameter, or I think we denoted this ds, is 2.5 meters. Our velocity of the stack gas is 20 meters per second, and our heat emissions rate is 30,000 kilojoules per second, which is also equal to 30 megawatts, which is what we need to use in the equation. Okay, so we're asked, first of all, to use the Holland formula. Now, I did provide some equations to you, but hopefully you already had those listed on your cheat sheet. But if you did not, the Holland formula is on the back right here, and this is the equation that we would be using. So that's our Holland formula right there. So we're going to copy that over to our sheet right here. So our delta H, which is our plume rise, is equal to 1.5 times the stack velocity times the diameter of the stack divided by U, and we'll talk about that in just a minute, plus 9.6 times our QH, which is our heat emissions rate, divided by U. Now, the U here is going to be the U, or the velocity of the wind, at this actual stack height. So we have to convert this wind speed that we'd have at 10 meters into a wind speed at this 80 meters up in the away from the ground. So to do that, first of all, we're going to use, well, we need to first find our stability class before we can get there. So we're going to look at table 20.1. We're going to find, if we can pull this up, that we are looking at, for example, a rural area. It's a cloudy night, so we're going to look here. We've got cloudy here, night conditions here, and then our surface wind speed is 3.2 meters, and so note it says, it even denotes here, it's measured at 10 meters above the ground, so this is what we need. So we look and see, okay, we're in this range right here, And so when we follow it over, we find we are in Class D stability conditions. So we know we have Class D conditions. And then next we can use our table 20.3 to find our p-value. What's our p-value? Well, we have our equation here that allows us to adjust wind speed from, say, 10 meters to 80 meters. And so notice we have one value here. This is the p-value. We need to look that up in our table. So we go back to this page, our table. Our stability class is D, and we are told here that this is a rural area. So we are going to go to our smooth surface, rural, and so we're going to go over, and our P then is 0.15. So we can write our p-value is 0.15. Now we'll copy over our equation for our wind speed adjustment, and our wind speed at 80 meters is equal to our wind speed at 10 meters times 80 meters divided by 10 meters, all of that to the 0.15 power. So that's just basically a rearrangement of the equation that we had on the back of the sheet for the two different wind speed values. And so we can go ahead and calculate this. So our U at 80 meters is going to be 4.37 meters per second. And so this, recall that this value here is our 3.2 meters per second. So if you put that in, we should be able to get the 4.37 meters per second. Okay, so now we should have everything we need to go ahead and calculate our plume rise. So our plume rise is 1.5 times 20 meters per second times 2.5 meters divided by 4.37 meters per second plus 9.6 times 30 megawatts divided by 3.2 meters per second. Our delta H is going to be 107 meters. So that is our estimated plume rise based on the Holland formula. All right, now we need to calculate steady state concentration at the following